All right, good morning, everybody. So we're talking about, first a quick announcement. So remember, assignment 1 is due at midnight tonight, although you do have that extra week if you need it. Assignment 2 should appear sometime tomorrow, probably tomorrow sometime. And so you also have roughly a week to do assignment 2. Assignment 2 picks up from where assignment 1 leaves off. So you'll want to, so assignment 2 picks up where assignment 1 leaves off, and at the end of assignment 2, you'll be able to actually see the game of life in action on your screens. At the end of the last class, we were talking about lists, and so we're going to finish talking about lists, hopefully today or the next lecture. If you have a list, you have a collection of elements. One of the common things you want to do with a collection of elements is you want to do something with each thing in the element. So you need some way to iterate over a collection. Iterating over a list is almost exactly the same as iterating over an array. Right? So you can use a for each loop with the list. Right? So here's a little snippet of code that tries to find the shortest string in a list of strings, non-empty list of strings. Right? So we start by assuming the shortest string is the first string in the list. Right? We get its length, and remember that as min length. And then we just look at every string in the list. Right? So we look at the first one twice, but that's okay. Right? So I can write a little for each loop. Right? For each string s, that's in t. Right? Inside the loop, s is just the string on the current. S is the string in the list for the current iteration. Right? So you just look at the length of the string. Right? Check if it's less than the minimum length. If it is, you have a new minimum length, then you have a new shortest string. Right? And away you go. Right? So just like iterating over an array. If you want to use a counting style loop, then again, it's just like iterating over an array. Right? So here, my for loop starts with int I equals 1. Right? I can start at 1 in this case because I've already looked at the length of string 0. Right? I is less than the size of the list. Right? Each time through the loop, increase I by 1. Now I'm using an index to access an element of the list. So to access an element of the list using an index, we need the get method. Right? So tGetI gets the ip element from the list and stores that in a string s. Right? And now the rest of the code is exactly the same. And if you want to, if you find yourself doing this over and over again or doing it more than once, then you just put it into a method. Right? So we make a little public static method that returns a string, which is the shortest string in this list t. Right? And now we can actually take care of the case where if the list is empty. Right? So if the list is empty, we throw an exception because there is no shortest string in an empty list. And then the rest of the code is exactly the same. Right? Choose either one of the two methods in this case. So you can either use a for each loop or you can use a counting style loop. And the code is the same either way. All right, so what else can you use a list for? So a more mathematical / scientific use of a list is for something like computing the odds of rolling a given number using a pair of dice. Right? So basically what I want to do is I want to use a list and I want to generate the following table. Right? Now if you've taken a stats course or if you've done any sort of basic probability, you know how to compute the odds of rolling any given number with 2 dice. Right? If you haven't taken a stats course, then one way to do this is to simulate rolling 2 dice. Right? So you roll 2 dice many, many, many times. Right? You count the number of times you see the number 2. Right? You count the number of times you see the sum 3. You count the number of times you see the sum 4, and so on up to 12. Right? Now, obviously, you can't roll a 0 or a 1 with 2 dice. Right? But the reason I'm putting 0 and 1 in this table is because I want to make a list. Right? So I want a list whose indexes go from 0 through 12. Right? And the index is just the value of the dice that were rolled. Right? So I'm going to make a list of length 13. Right? The first 2 elements will be 0 in the list. Right? And then hopefully each successive element in the list is the number of times we roll 2, the number of times we roll 3, and so on, and so on, and so on. Okay, so how do you simulate rolling 2 dice? Well, you need to be able to generate a random number. Right? So there's a class called random. It's in the package java.util. And that class lets you generate random booleans, random ints, random doubles, floats, and longs. Right? If you're curious as to how you generate a random number on a computer, you can click that link there. If you want to know more about the class random, you can click that link there, and that'll take you to the documentation. Okay, so to compute the odds numerically, what we're going to do is we're going to perform these 3 steps. I want to make a list, right? And I want to add 13 zeros to the list. So basically, I want to make this list over here, right? Its length is 13, and I'm going to populate all the elements with zeros to start with. Right? Then I'm going to do the following n times, right? Where n is some large number. Right? I'm going to simulate rolling 2 dice. I'm going to do that by using the random class. Right? And I'm going to compute their sum. Right? So suppose I roll a 8. Right? I'm going to go into the list. Right? Look at element number 8, which will be a 0 to begin with. Right? I'm going to add 1 to that value and put it back into the list. So now there'll be a 1. Right? And then I'm going to repeat the process. Right? So now the next time I roll, say, a 12, I'm going to go into the list. Right? Look at what's here at index 12, so there should be a 0 there. Right? I'm going to add 1 to it and store it back in the list, so now there'll be a 1. And I'm just going to do this over and over and over again. Right? At the end, we can divide each element in the list by n, and that will give us the percent odds. Right? So let's do this in Eclipse. Right? All right, so you make a little class. It doesn't matter what you call it. Right? I've called it dice odds. You stick a little main method in the class. Right? And now you just start to follow those steps that were given in that algorithm. Right? So we make first step is make an array list. Right? So array list. Okay, when you make an array list, you have to decide what values are we storing in the list. So I'm storing the counts, so it makes sense to use an integer in this case. Right? And these are just the counts, so I'm just going to call the variable, I'm just going to name it count. Right? Call the constructor, so new array list. And I want to start out with an empty list. Right? Step 2, I need to make a list and I want to put in 13 zeros into the list. Right? So I want to make, where is it? Right here. I want to make this list here, right? With all of these values equal to 0 to begin with. And so all we need there is a loop that runs 13 times. Right? So, whoa, sorry. Right, now in a little program like this, it doesn't matter that you're using this number 13, right? So if you've done some previous programming before, someone might have told you that that's a magic number, right? It's just a number that appears out of nowhere. Which is true, so you could give it a name if you wanted to, right? Name it as a constant. So you do something like final int, let's do max value, and we're going to set this to 12 now. So we'll have to change that to that. Whoops, sorry. Okay, so that keyword final, I don't remember if I told you what that means. In Java, the word final, when you apply it to a variable, it means you can only give the variable a value one time. Right? You don't have to do it here. Right? So I don't have to say equals 12 here. I can just put a semicolon. Right? But when I assign a value to max value, I can only do it once. If I try to do it a second time or a third time, the compiler will complain. Right? And so you can't assign a value to a final variable. Right? And so in this case, max value is a constant. Right? Making it final makes sense in this case so that I don't accidentally change it somewhere else in my code. Right? If you have a constant value, then those are often shown as all caps. They're often written in all caps. Okay, so stylistically this is slightly better, but in a program this size, it doesn't really matter. Right? Now populate the list with zeros. Right? So count.add. Oops, sorry, 0, like that. Okay, so there's my list of 13 zeros, and now I can write a loop that runs n times. Right? So again, n's a constant, so it kind of makes sense to make it a constant. So n equals. So we need to do this many times. I don't know. So we'll pick some value to begin with. So we'll start with 100. And then you write a loop that runs n times. So like that. Right? Now I need to roll 2 dice. So I need a random number generator. All right. So I could write this inside the loop. So I could make a random object. So random RNG, so random number generator equals new random. Right? So I could write that. Sorry, let me strike these two first. Okay. So if you start out with the program as a brand new empty editor file, when you write array list the first time, your compiler is going to complain. Right? It's going to say, I don't know what an array list is. That's because you have to import it. Right? So you have to import the class array list. Eclipse will often suggest a class to import. For array list, it's fine. You can pick the suggestion. There are a few other types where you have to be careful. It doesn't always pick the right type. Right? And so if you do that, it automatically inserts the import for you. Similarly for random, it's going to complain, I don't know what random is. Right? So you have to import random as well. Again, this is the correct suggestion, so we can import that. Right? Both array list and random are in the package java.util. So I could do that. Now the problem with doing that is that inside the loop, every time the loop runs, I make a new random number generator object, which is wasteful, because I could just use the same object to generate random numbers. So I don't want to make the random number generator inside the loop. I actually want to make it before the loop. Right? And now inside the loop, I can just use the random number generator to generate my random numbers. So inside the loop, I need to generate 2 values between 1 and 6. Right? So int, I guess D1 for die1. So I'm going to ask the random number object, the random object to give me a new random integer value. Right? And so the method for that is nextInt. And you can see, you might be able to see it's small for you at the back. There's 2 choices for nextInt. Right? Your first choice for nextInt has no, there are no arguments to the method. Right? So that generates a random number between integer min value and integer max value, which doesn't help us in this case. Right? I want a number between 1 and 6. So I need the next version of the method. So the next version of the method, you pass in an integer value, and you get a random number between 0 and that value minus 1. Right? So if I pass in 6, I get a random number between 0 and 5, which is almost what I want. Right? If I want a number between 1 and 6, I just add 1 to the result. And there you go. Right? So there's your random number between 1 and 6. I need 2 of those. So just copy that line, call it D2 for dice 2. And there are my 2 randomly rolled dice, or dice values. Right? Now compute their sum. Right? And now look up the sum in the list. Right? So int. So the current count for sum is just the list count get sum. Right? So go into the list, see how many times I've rolled the sum. I want to add 1 to it and put it back in the list. Right? So to put it back in the list, it's count set. Right? So I want to set the sum to cur count plus 1. Right? And that's it. That's the body of your loop. Right? Now obviously you could write that in fewer lines with fewer variables. Right? But I've written it that way so that you actually see each step written out explicitly. And when we're done, for now, let's just print out the list and see what we get. Right? So to print a list, you can just print it using printline. Count, like that. Right? And there's your little simulation. Right? So if we run it, we get back the values 0, 0, so that's good, right? I rolled 0, 0 times. We rolled 1, 0 times, right? We rolled 2, 7 times, 3, 5 times, and so on and so on and so forth. So those results don't look exactly right, right? We should get a peak at 7. So 2, 3, 4, 5, 6, 7, and we don't quite get a peak at 7. But that's because we didn't run the simulation enough times, right? So if you crank n up to say 1,000,000, right? Even on my laptop, this takes no time to run, right? Click the button and away you go, right? And now you get some numbers here. So this is 2, 3, 4, 5, 6, 7, right? And if you look at the numbers, that does in fact look like the highest value, right? So you most often roll 7. You should roll 6 and 8, the same number of times, and it looks like, yeah, that's roughly the case, right? You should roll 5 and 9, the same number of times, and so on and so on and so forth, right? If you want to get the odds, just divide everything by 100. By n, right? So if I want to divide everything by n, you just write it down a little loop. Oh, so yeah, for int I equals 0, I is less than or equal to max. Right, and so now I'm going to take count. I'm going to set the element at index I to the current value. So let's just count, get I, divided by n. Right, and now I'm going to print out count here. Okay, so run that. And we get all zeros, which not right, right? So you ask yourself, well, why did I get all zeros? Why did we get all zeros? Yep, at the back. Yeah, right. So because our array list holds integer values, that's an integer, right? It's less than n for sure, right? So when I take an integer and divide it by n, where n is bigger than the integer, you get 0 point something. It's integer arithmetic, so throw away the point something, and you get 0 every time. Right? We can fix this pretty easily. I just go back and change this to double. Right? Okay, and now we take a look. Right? We've got some problems here. Well, we have some warnings here. Actually, we have some errors here. Right? So it says here, when you add this element to the list, right, I can't add the number 0 to your list of doubles. Right? You say, well, that's weird. 0's convertible to double. How come I can't do that? Right? And so the answer is because of Java's generic mechanism. Right? So this is an array list of big D double. Right? So normally I can pass in a little d double value and have it work. But the number 0 as a literal, right, is not a little d double value. Right? It's a little I int value. So we have to tell the compiler that this is in fact a double value. So 0.0, that's the easiest way to do it. Right? So that error goes away. Right? Now we've got this error here. Right? We say get. Right? So when I get a value out of the list, it's a double. So I can't store that in an int. So I have to change that to double. Right? Now the next error goes away, which is good because cur count was an int. Right? I can't store an int in a list of double. Right? I have to store a double in a list of double. And now everything's fine. So now we can run that. Okay, now when we run that, we get 0, 0. So that's 0.027708. And the correct answer is 2.78%, which is pretty close to 0.027708. Right, next number is 5.5695. And the correct answer is 5.56. Right, which is pretty close to that. Right, and so on and so on and so forth. Right, so if you actually look at the numbers, they do actually closely match what's on the expected results. As you increase the value of n, right, more and more and more and more, you'll get closer and closer and closer to the true odds. Right, so that's a little example of how to simulate a random event. It's a simple example, but the underlying principle, where you generate random values many, many times, and then compute an average or something like that. That's actually how many simulations are run for science and engineering applications. Okay, any questions about that little piece of code? All right, let's carry on. Okay, so let's do another little, instead of working this all out in Eclipse, I'm just going to describe the problem and then I'll show you the answer. Right? So if you flip a fair coin n times, right, there's many questions you can ask about the outcome. Right? So you might ask, how many heads do you expect to see? Right? Well, if it's fair, you expect to see n over 2 heads. Right? You might ask the question, how often do you expect to see n over 4 heads? Or how many times do you see 1 head? Or how many times do you see no heads? Right? Or something like that. Right? If you've studied this problem in a statistics course, you know that this follows the binomial distribution. Right? The setup of the problem is similar. Right? I'm going to make a table of n plus 1 values, right? Where the index corresponds to the number of times we've seen a head, right? After rolling the coin n times. Right? So to compute the odds, you're going to do the following, right? Make your list, add n plus 1 zeros to the list. Then you're going to, you're going to repeat m times, right? So what I want to do is I want to repeat, I want to flip a coin n times, and I want to do this many times, right? So my m, that's the many times, right? So inside this loop here, I'm going to have another loop where we flip the coin n times, right? And we're going to count how many heads we get, right? So that's the variable count here, right? So count is the number of heads we see for one trial of flipping the coin n times, right? After flipping the coin n times, you have some count. So you're just going to go into the list, find the entry corresponding to the count, and add 1 to that value. Right? Then at the end, you can divide each element in the list by m. Right? So there is in the next deck of slides, the answer is there. Lists, which one is it? 8, 9. So it's right here. Right, so I'm going to simulate flipping a coin 20 times. Right, how many times am I going to do that? I'm going to do that 1,000,000 times, it looks like. Right, I'm going to make my list to store the value for 0, 1, 2, 3, 4 up to 20. Right, so there's my little loop that adds 0 21 times to that list. Right, there's my random number generator. Here's my loop that flips the coin, that does the flipping of the coins 20 times m times. Right. Inside the loop, there's another loop that actually flips the coin n times. Right. Now, how do you simulate flipping a coin? Well, it's one of 2 results. Right. So I can use next Boolean to simulate flipping the coin. Right. Next Boolean randomly returns true or false. So every time it returns true, I'm going to assume that's a head and add 1 to the count. Right? After flipping the coin n times, go into the list, right? Get the number of times you've seen that many heads, add 1 to it, and put it back in the list using set. Right? And at the end, we can divide everything by the value m to get the cumulative probability. Right? So if you run that, you'll actually get the cumulative probabilities. I don't think I showed you the output here. No, I don't. So if you actually run that program there, you can generate the estimates of the probability of rolling a head some number of times, given that you flipped it n times. Right? And so there's another example of using a list and the random class to generate random values. Okay. Any questions so far? Yes? No, you could use an array, but we're talking about lists, so it makes sense to use a list in this case. Yeah, but you could use an array. An array is appropriate here, actually, because you know the number of you know the number of entries in the array, and it never changes. Yeah. All right, so we're going to do a little bit of recursion with lists now. So we got this little not terribly fun game called Jump It. So jump it is made up, it's just a linear board, right? So it's a board of n squares, right? Where n is greater than or equal to 2. Right? The way you play this game is you always start on the leftmost square, right? On each move, you're allowed to move 1 or 2 squares to the right, right? So starting at 0, I can move to the 3 or the 80, right? Your goal is to make it to the last square of the board with the lowest cost, right? Every time you step on a square, the value that's in the square is the cost of stepping on that square, right? So you would like to reach the end with the smallest cost, right? So for this example, this is not a very hard example, right? You would move 1 square, right? So your cost is 3, right? You'd move a second square. You'd move 2 squares now, so your cost is now 9, and then you'd move 2 more squares to the 10, so your cost is now 19. Right? Okay, so how did I get that solution? Well, the board is small enough that you can eyeball the solution, right? But if you had to come up with a general algorithm for doing this, the way you might think about doing this is look at the square that's 1 to the right and look at the square that's 2 to the right, right? And then pick the one that's smaller, right? So this is what we call a greedy algorithm, right? You choose the next step that minimizes the current cost, right? And it looks like the greedy algorithm actually works here, right? My choice is between the 30 and the 80, so the 3 and the 80, so I'm going to pick 3. Right? Now my choice is between 80 and 6, so I'm going to pick 6. And now my choice is between 57 and 10, so I'm going to pick 10. Right? Now the question is, does this always work? Right? And the answer is no, because it might be better to move to a square with a higher cost because you would have ended up on that square anyway. Right? So suppose we get to the 17 on this board. Right? If you choose the greedy algorithm, you're always going to pick the square with the next lowest cost. Right? So your choice is the 1 or the 5, so I'm going to go to the 1. Right? Now your choice is the 5 and the 6, so I'm going to go to the 5. But I could have gotten to that 5 from the first step. Right? So your total cost here ends up being 24, whereas the optimal cost is actually 23 in this case. Right? And so you can't just pick the square with the lowest cost and hope to get the correct solution. Sorry, and be guaranteed to get the correct solution. Right? So in fact, what you have to do is you actually have to look at all combinations of moves. Right? And if you try to do that with just a regular for loop, or even a nested pair of for loops, you'll quickly discover that you can't write the solution for the problem that way. Right? Because at every step, you've got one of 2 choices. Right? So if you have to take n steps, you have to evaluate 2 to the n possible steps, possible moves. Right? Okay, so how are we going to solve this problem? So let's try to solve it using recursion. Right? All right, so whenever you're faced with a problem and you're told it's a recursive problem, well, whenever you're faced with a problem in general, it's always useful to sketch out a small example of the problem. Right? In recursion, it's particularly helpful because it helps you find the base cases and it helps you find the recursive cases. Right? All right, so remember the base cases, those are the cases where you know the answer to the problem. Right? So what are your base cases in the jump it problem? Right? Well, the smallest board size is 2. And I know if the board size is 2, there's only one possible move. Right? So I know the answer if the board size is 2. Right? If the board size is 2, then the cost is just the current square that you're on plus the last square of the board. So that's easy. Right? If your board size is 3, you also know the answer. Right? You're on the first square, I need to get to the third square, I just skip the second square. And so your answer is just start on the first square and jump straight to the last square. And that's your answer. Right? And so that wasn't too bad, right? We've got our base cases. Right? And so when you go to write up your solution, right, for a recursive algorithm, right, typically the base cases go first. Right? So I'm going to represent my board using a list of integer. Right? My method cost returns the smallest cost for solving that board. Right? So the smallest cost for solving that board. Right? So my base cases are if the board size is 2, then it's just the sum of the 2 squares. right? And if the board size is 3, it's the sum of the first and last square, right? And now we have our recursive case, right? So your recursive cases are, right? I can move, what happens if I move 1 square to the right, right? What is the cost of the rest of the board, right? The second recursive case is, well, suppose I move 2 squares to the right. What is the cost of the rest of the board, right? So those are your 2 choices at every step, right? What is the cost of the rest of the board, you can solve that problem recursively, because that's the method you're writing right now, right? The cost is the cost of solving that board, right? So if I can somehow compute the rest of the board, I can just recursively call the method, and it'll solve the problem for me. Right? So after 1 step, so I want to compute the board after taking 1 step to the right. Right? So what is the board after taking 1 step to the right? Well, I could remove the first element from the board, but that's dumb, right? Because there's this sublist method right here. Right? Sublist gives you the part of the list that you ask for. Right? So if I ask for the sublist starting at index 1, right, going up to and including the last element of the board, right, that gives me the rest of the board after taking 1 step. Right? Similarly, if I ask for the sublist starting at index 2, going up to, but not including the size of the board, right? So starting at index 2, the rest of the board, right? That gives me the rest of the board after taking 2 steps. Right? My current cost, that's just the square that I'm currently on. Right? So that's just the value of the board on the current square. Right? Now how do I compute the cost of solving that board? Right? Well, the cost method computes the cost, the minimum cost of solving a board. So I can just call cost, passing in the board after taking 1 step. Right? How do I compute the cost of solving the board after you take 2 steps? Well, cost computes the minimum cost of solving a given board. So I can just call cost, passing in the board after taking 2 steps. Right? So recursion solves that, recursion solves that. So you get a minimum cost for after taking 1 step. You get a minimum cost after taking 2 steps. The smallest possible cost is the smallest of those 2. So I can just compute the min of those 2 and add that to C, and that's your minimum cost solution. Right? All right, so I've been told you've done recursion in 121. So does anybody have any questions about that solution? Is everybody confident you could write that solution? Yes, maybe, no, yes, sort of, kind of. So that's the first time we've seen sublist, right? And so there's a good example of using sublist, right? If you want part of a list, then sublist, you should consider using sublist. Right? So I claim that that will in fact solve the jump it problem. Okay, so you can get a little more fancy here, right? So it's great that you can compute the minimum cost, but it would be nice if you could compute the actual sequence of steps that you would make to get the minimum cost, right? So can you modify that method so that it actually produces the list of moves, right? So here, right, to solve this board, I take 1 step, then 2 steps, and then 2 steps. So can you modify the method so that it returns the minimum cost and it also produces the list 1, 2, 2, right? So that is what we like to call an exercise for the student, right? So I suggest you use the following method, right? So write the method cost. It takes in a board. It also takes in a list called moves, right? And so what cost is going to do, it's going to fill in this list called moves, right? When you call the method the first time, moves should be empty, right? And then cost should fill in the list of moves as it progresses towards the solution, right? And then return the minimum cost. Okay, so jump it has a couple of nice problems. A couple of nice properties, right? The rules of the game make it impossible to move to the same square twice, right? You're always moving to the right. Furthermore, the rules of the game make it impossible to try to jump off the ends of the board, right? So I never fall off the left end, I never fall off the right end, right? So we can make the problem a little harder where neither of these two things are true, right? So now I've got a board. All the values are non-negative. The last one's always 0, right? So I want to start on the left-hand side, and I want to try to reach the right-hand side. Right? Here we're not interested in the shortest sequence. We just want to try to get to the right-hand side. Right? Now the number on each square, that's the number of squares you can move left or right each time. So starting at the 2, I'm allowed to move 2 squares left or right, but I have to stay on the board. Right? So I can move to the 4. Right? Now that 4 says I can move 4 squares left or right, but I have to stay on the board. So I have to move to the right, 1, 2, 3, 4. Right? When I get to the 1, I am allowed to move 1 square left or right. So I can go to the 2 or the 6, and so on and so on and so forth. Right? And so can we solve this problem now? Right? So to solve this board, we go 2 to the right, right? Then 4 to the right. So now I'm at the 1. Now I have a decision to make. Right? So do I go left or right? Well, let's try going right. Right? I end up at the 6. Can't go right, right? Because I fall off the right-hand side of the board. So I have to go left. Right? And that gets me to the 4, right? The 4, I can't go left. So I'm at the 1, and I'm at the 6. Wait, what happened here? Did I screw that up? 6, sorry. 6 in the, sorry. Oh, there. I'm going the wrong way. Sorry. 6 to the 3. Right? Can't go left, so I have to go right. Right? 5 still can't go left, so I have to go right, but I end up at the solution here. Right? There's another solution, though. Right? So starting at the 2, I can go to the 4, then to the 1. Now I can go left instead of going right. So I can go to the 2. Right? At the 2, I now have 2 decisions. Right? I can go to the 6, or I can go to the other 2. Right? So let's go to the other 2. Right? And now I can go to the 3, or I can go back to the other 2. Right? And so that probably doesn't make sense. Right? It probably doesn't make sense to backtrack and go to a square you've landed on before. Right? Because that doesn't actually progress you towards a solution. So here I'm going to go left. Right? And now I'm at 3, so I go to the 5, and now I go to the answer. Right? So it turns out there's at least 2 solutions on this board. There's probably more, but there's at least 2. Right? So that example there illustrates the fact that you can end up in what's called a cycle. Right? So I can end up just going around and around and around because I end up on squares that I've already visited before. Right? The cycle doesn't have to be one step. Right? I might go from one square to another square, then that square to another square, and then back to the starting square, then back to the first square. Right? So if you have cycles on your board, you can easily make a board where no solution exists. Right? So that board has no solution because I just end up going back and forth between the 2's. Right? And on this board here, no matter what you try to do, you end up on a cycle. Right? You end up in some sort of cycle. So there's no solution on this board either. And even without cycles, it's easy to make a board where there's no possible solution. Right? So if I have a 1 here, 1 here, right? I can only go to the 100. Once I hit the 100, I can't go either way, right? Because I fall off either end of the board. All right, so how do we solve this particular problem? So when you solve a problem recursively, one of the things that must be true in order to guarantee a solution is that every time you recurse, the problem that you're solving has to get smaller in some way. Right? So in Jump It, we're always moving to the right. Right? So our board is always getting smaller and smaller and smaller. Right? And so that satisfies the decreasing size problem, the decreasing size of the problem property. Right? Now in this problem here, right, it's not exactly clear that the board gets smaller at each step, right? But in fact it does, right? So it doesn't look like the board gets smaller, but you don't want to end up on a square that you've already been on, right? So every time you land on a square, you want to rule that out as you want to rule that square out as part of a possible future solution, right? So in fact, every time you take a step, the board gets smaller by size 1. So it looks like there might be a possible recursive solution here. Right? And so what we need some way to indicate that we've actually been on a square before. Right? So again, let's try to solve this using recursion. Right? Okay, so what are our recursive cases? Right, so I'm not starting at the base case this time. This time I'm going to start at the recursive cases. Right? So in the recursive case, right, you want to ask yourself, can I move left? Right? If you can move left without falling off the board, right, then go ahead and move left, and then ask yourself, well, can I solve the problem from this square? Right? Similarly, right, when you're on a square, the second recursive case is, well, can you move right without falling off the board? If you can, move right, and then try to solve the board from the next square. Right. Okay, so this is the method I'm going to use to solve this problem recursively. So the method is called isSolvable. It returns true if that board is solvable starting from that location of the board. Right? It returns false otherwise. Right? So the first time you call this method, index will be 0, right? And you'll pass in the complete board. Right? Oh, notice up here, the method does not permanently modify the board. Right? It says it doesn't modify the board, but that really means it doesn't permanently modify the board. Right? So in other words, whoever calls this method, when the method returns, their board appears to be unchanged to the caller. Right? So I'm going to start this one by not writing the base cases. Instead, I'm going to write the recursive cases, because the recursive cases are slightly easier in this case. Right? So I'm going to start by looking at the current value of the board where I'm standing right now. Right? So I'm going to get the value of the board at that index. Right? And that tells me how many squares left or right I can move. Right? I now want to indicate that I've been on this square before. Right? And so the way I'm going to do that is I'm going to temporarily modify the board. Right? Remember, I can't permanently modify the board, but I am allowed to temporarily modify it. So I'm going to set the current square that I'm on to -1, right? Because all of the valid squares of the board, their values are positive. Right? So I can use a negative value here to indicate that I've been on the square before. Right? Notice there's a comment here, right? So remember, I have to undo this change before this method finishes. Right? Okay, now, can I go to the left? Right? So how do you test, can I go to the left? Well, I'm currently on that index of the board. Right? Value is the number of steps that I can move. Right? If I move left, the index goes down, right? So moving value squares to the left, my new index is index minus value, right? So if that index is bigger than or equal to 0, it's a valid index, right? If it's less than 0, it's not, and I can't go left, right? So if that's a valid index, go ahead and move left, right? So in other words, ask, is the board solvable if I move to the square to the left on the newly modified board, right? I've marked that board with a -1 on it, right? And that will return true or false, right? I can do the same thing to go right, right? So can I move by going right, right? Well, how do I move? Can I move right? Well, if I move right, I need to move value squares to the right, right? So the new index is index plus value, right? To be a valid index, that must be less than the size of the board. So if that's true, go ahead and move right, right? So when right becomes isSolvable, index plus value on the modified board, right? Because I've marked it with a 1. Right? Okay, after I've recursively done this, right, I've got an answer, right? I have to undo the change that I made here, right? So set the board back at that index to that value, right? And I know that the answer is win left or win right. Right? If either one of those is true, then I can solve the board by going. Then I can solve the board. Right? If they're both false, the answer is false. All right. Any questions there? Still have to do the base cases. Okay. So what are the base cases here? So how do I know that I can actually solve this board? So there's two base cases in this case, right? So this method returns a Boolean, right? So it returns true or false, right? Now what that means for your recursive method is that there's probably at least two base cases, one of which returns false, one of which returns true, right? If you find yourself writing this method and you only have one base case, right? So in other words, it always returns true, or the base case always returns true, or it always returns false, there's probably something wrong, right? So we've got one base case. So if I jump to a square that's got a -1 on it, I'm in a cycle, right? So the board's not solvable by taking that step, right? Which means I can return false. So there's my false base case. Now what about the true base case? Well, the true base case is when I end up on the final square, right? So if I end up on the last square, then yeah, the answer is true, right? And there are your two base cases, right? Which are easy to code up, right? So if the board value at that index is less than 0, I've been on this square before, I can't solve the board taking that step, right? If I end up on the last square of the board, I've solved the board, so we return true, right? And I claim that that plus that correctly solves this problem. Okay, I think that's enough for today. Yeah, we're past quarter after, and we'll pick this up in the next lecture. Right, so there'll be more recursive methods on lists in the next lecture.